Floyd Warshall Algorithm. It is an algorithm for finding the shortest path in a weighted graph with positive or negative edge weights but with no negative cycles. And it finds the shortest path between all the pair of vertices. And this is published in its current form by Robert Floyd in 1962. Let's see its real life application, which is in tourism. Shilpa is a girl from India who had a wish list to visit some of the important places in India, and that included Tawang, Manali, and Kanyakumari. But she has very less time and she's pretty smart. She wanted to figure out, okay, like which places should I visit first or which order should I follow so that I can visit all the places in the shortest possible time. That is, she wanted to find the shortest route between all these locations and she's willing to start from any location. So she wanted to figure out if she starts from each of these locations differently, how long will it take to reach the other places from there. So she uses Floyd Warshall algorithm to achieve the same. So the problem is first framed as a network. So Manali is given vertex 1, Tawang as vertex 3, Kanyakumari as vertex 2. And the edge weights denote the distance between them in a hypothetical sense. For this, first we construct a D naught matrix, that is a distance matrix. Here, the distance between 1 to 1 is 0, like she doesn't have to go to the same place again, obviously. So, all the such places like 1 to 1, 2 to 2, and 3 to 3 have been indicated as dashed lines, and the distance between 1 to 2 given by the edge between them is 5. Distance between 1 to 3 given by the edge between them is 2. So likewise this matrix has been constructed. Similarly, S naught is a vertex sequence matrix. So initially the value from for this S naught matrix is given as the row headers. Now, since we have three vertices, we'll have to iterate four steps. That is, we need to find D1, D2, and D3 simultaneously S1, S2, and S3. Now, let's find out how to find the D1 matrix, which is the next iteration. Here, we have to fix the first row and first column. That is, since it's D1, we have to keep the first row and first column from the previous D naught matrix as it is, and vary only the remaining values, and diagonal values will also remain unchanged. So now the only values which are under considerations are 2 to 3 and 3 to 2. And since it's an undirected graph, both values will be same. So we consider 2 to 3. Now from 2 to 3, we'll have to check what if we reach 3 from 2 via 1. So the value in the previous matrix for 2 to 1 was nothing but 5 and 1 to 3 was 2. So their sum was 7. So if we want to reach 2 to 3 via 7, the distance is 7. Whereas to reach directly from 2 to 3, the distance taken is just 1, which is the minimum. 1 is the minimum. So we keep 1 as it is, and hence our D1 matrix has not undergone any change. It's same as the D naught matrix. And since there is no change from the previous matrix, the S1 matrix also remains as it is by as given in the S naught matrix. Now we proceed to D2 matrix. Here we keep the second row and second column fixed and diagonal also fixed. Now we consider D13 element, that is the distance between 1 and 3. So, if we want to start from 1 and reach 3 via 2, let's check the distance from the previous matrix, which was 1 to 2 was 5 and 2 to 3 was 1. So 5 plus 1 is 6, which is again greater than directly going from 1 to 3, which is 2. So again, we keep the minimum value here as 2, and we do not change the matrix any further. And since it's a symmetric matrix, D1 3 value is same as D3 1 value. And the matrix came symmetric because of the undirected nature of the graph. Now, since again D2 underwent no change from D1, S2 is also same as S1, no change. Here we reach the final step of our process and we need to find D3 and S3 matrix. So for D3 matrix, we need to keep the third row and third column fixed as well as the diagonal elements fixed. So the only elements we need to consider are 1 to 2 and 2 to 1, and since it's an undirected graph, these two values will remain same. So let's consider the distance from 1 to 2, and this distance from the previous matrix is actually 5. That is, the direct distance to reach 2 from 1 is 5. But what if we reach 2 from 1 via 3? That's what has to be investigated at this step. So if we want to reach 2 via 3 from 1, we check the distance between 1 to 3, which is 2, and from 3 to 2, which is 1. So the sum is 3. So if we want to reach from 1 to 2 via 3, the distance is actually 3. But the direct distance between 1 to 2 is 5, which is minimum. We'll have to consider the minimum ones because we want to minimize distance and minimize our time. So we take the root of reaching to via 3, which is 3. So the value of 5 from the previous matrix has been replaced to 3, and hence the 2 to 1 value is also changed to 3. Thus, we have obtained a D3 matrix which is not same as D2. We have edited two values. So its corresponding values in the S3 matrix should also be edited. But how? Since it's D3 step, so this 1 to 2 in S3, which has been edited in D3 matrix, so the corresponding S3 matrix will also have its value edited to 3. So since it's S3 step, the 3 has to be replaced in the position from 1 to 2 and 2 to 1 in the S3 matrix. Now we have obtained the final D3 and S3 matrix. So this D3 matrix gives us the distance between the corresponding vertices, and this distance is the shortest distance. So the shortest distance from 1 to 2 is 3, from 1 to 3 is 2, from 2 to 3 is 1. So this information has been obtained from this D3 matrix. Now, what does this corresponding S3 matrix indicates? See, the S3 value from 1 to 3 is 3. That is, if the S3 value from ith place to jth place is equal to j itself, then the I to jth root is the shortest route. But if it's not so, we'll have to find the in between roots. So here the value of S3 from 1 to 3 is 3. That means the shortest route between 1 to 3 is 1 to 3 only. Similarly, the route between say 2 to 3 is 3 itself. So the shortest route between 2 to 3 is 2 to 3 only. We need not have to go via another vertex. But let's check at the value of 1 to 2. So the value of 1 to 2 is 3 and not 2. Hence, the direct route 1 to 2 is not the shortest. So we'll have to consider the in-between vertex. Now, since 1 to 2 value is 3, let's check the value of 1 to 3. So 1 to 3 is 3. Hence, we log this value. So the actual route to reach 1 to 2 in the shortest way is go from 1 to 3 and then from 3 to 2. And hence, we have obtained the shortest distance between all the vertices as well as the shortest route between all the vertices available, and hence we have achieved the goal which has been bothering Shilpa, and we have given a good solution through Floyd Warshall algorithm.